Alright class, back in Chem 1A, do you remember we said when we add a solid to water, it will either dissolve or not dissolve. For example, we say if we take NaCl, and if you add NaCl solid to water, that's going to dissolve in water and break up into ions. And then we said if you get, for example, lead 2 iodide, and you add it to water, lead 2 iodide would not dissolve in water, it would stay a solid. But these would be AQ because they would dissolve and break up in water. Okay, now we sort of lied to you in Chem 1A. So, for example, lead 2 iodide, it is insoluble when you add it to water. It wouldn't dissolve. We call it insoluble, but in reality, everything does ionize to some degree. Even if we call it insoluble, but it does ionize to a very small degree, but some of it will ionize and will break up and dissolve in water. So, what we're going to talk about today is solubility product constant. So, we're going to talk about solubility product constant. And this has to do with insoluble solids that we told you guys that would not dissolve in water. But now we know to some degree, very small degree, they will dissolve. Now, solubility product constant are called KSP. Okay? Now, where have you seen K before? You know what K is. That's the equilibrium constant, right? And SP means solubility product. So, KSP is an equilibrium constant for compounds that will only slightly dissolve in water. So, this would be, let me actually write it down. So, the equilibrium constant. Again, it's an equilibrium constant. And it's an equilibrium constant for slightly soluble compounds. Actually, I'm going to even write that down too. For slightly soluble compounds. So you know when we use this. When we have compounds that are only slightly soluble in water. Okay. Now, we've already done this before. You completely get this. You completely got this. Lead 2 sulfide is a solid. Now, because lead 2 sulfide is a solid, okay, I'm going to have an equilibrium for it. And some of it, not much, but some of it will break up into ions. Some of it will break up into ions. So you can look at the solubility rules. When the solubility rule says it's insoluble, but we know that it will be slightly soluble, and we can write an equilibrium for it. Okay. Now, since I have an equilibrium, I can write an equilibrium expression. Equilibrium, any kind of K, Ka, Kb, Kw, they were all product over reactant. Concentration of product over the concentration of reactant, with one key thing to remember, that solid and liquid were not included in equilibrium. Okay, so my product is a concentration of lead 2 iodide times concentration of sulfide iodide, but what is my reactant? Is a solid, so I'm not going to include solid in the equilibrium expression. It's product over reactant, but my reactant is solid and liquid are not included. So this would be my KSP. So far so good? Okay. Now, let's do another one. Magnesium hydroxide. If you look at the solubility rule, it says is insoluble. Can you write an equilibrium for a KSP for this and write the KSP expression? So pause my video, and then write down the equilibrium equation and the KSP expression for me. So hopefully this is what you did. Now you unpause me. I'm going to write an equilibrium. Mg plus 2 and 2 OH minus, right? Because when this breaks up, I have an Mg plus 2, and I have 2 OH minus when this breaks up. Okay, so the Ksp is going to equal concentration of magnesium ion times concentration of hydroxide ion to the power of 2, right? This is just like equilibriums before. The K expression was product over reactant, concentration of product over the concentration of reactant, and you had to care about the coefficient. Those would be the power. And this is a 2, so the 2 goes over here. So let's do one more. Let's do one more to make sure you get this down. So do the same thing for zinc phosphate. You probably, in case if you don't remember what's the formula for zinc phosphate, Zn3PO4 2. So write down the equilibrium and the equilibrium expression. Okay, hopefully you paused me and you did this. When this breaks up, it would be, how many zinc do I have? I have 3 zinc, right? So it would break up into ion, zinc plus 2. Now remember, when they break up into ions. They break up into ions. Now the zinc is plus 2 because this is where, when you cross multiply the charges, this is where the 2 come from. Now I have 3 zinc plus, how many phosphate do I have? I have 2 phosphate. What's the charge on phosphate? Is minus 3. If you don't remember your polyatomic ion, you can also kind of figure out from the whole formula. And you go, okay, the 3 came from the phosphate, the 2 came from the zinc. So this is my ions. So when I break up into ions, you have to, don't forget the charges. They break up into ions. All right, again, it's the equilibrium. Not all of them are going to break up because this is an insoluble solid, but some of it will break up. Now, the Ksp expression is going to be the zinc concentration to the power of 3 times the phosphate concentration to the power of 2. One more time. Again, when we look at the solubility rules, when it says something is insoluble, like zinc phosphate, magnesium hydroxide, lead 2 sulfide, but we know some of it will be slightly soluble. So some of it will break up into ion. And that's when we have an equilibrium going on, because some of it, to a few degrees, will break up, but most of it will stay together. So we can write an equilibrium for it and an equilibrium expression. But solid and liquid are not part of the equilibrium expression. Okay, so far so good. Now let's do a practice problem. Okay, let's do a practice problem with this. Our first practice problem is going to be this one. Lead 2 sulfide has a Ksp of 8.4 times 10 to the minus 8. What is the molar solubility of PBS? Okay. The best way to learn Ksp is by doing practice problems. So let's do this. All right. Now, basically, before we do this, what is molar solubility? I just introduced that. What is molar solubility? Is the max amount of solid dissolved in a water, in 1 liter of water. Basically, what is the max of this solid I can dissolve in 1 liter of water? Okay, what is the max amount I can dissolve in 1 liter of water? That is my molar solubility. How much of this could dissolve? What's the max that it could dissolve in water? Okay, so it would be max amount dissolved in water. Now, every time you have Ksp, and I want you to do this every time, you go, all right, I have a PBS. I'm going to write down the equilibrium equation. Some of it will break up into PB plus 2 and S minus 2. Okay. And my Ksp is going to be concentration of lead ion times concentration of sulfide ion. do this every time. Now, do you remember in any KSP, we usually go minus x, x and x? Yeah? This is exactly the same thing. Again, PBS, because it's a solid, it will not be part of this equation. So in that case, I have the KSP. What is my KSP? My KSP is 8.4 times 10 to the minus 28. PB is x, and my sulfide ion is x, right? So it would be 8.4 times 10 to the minus 28 equals x squared. Now, if I solve for x, what I end up getting is 2.9 times 10 to the minus 14. Okay, now let's talk about what is this x. What is this x? What does this x mean? So the x is molar solubility, right? So it's basically molar solubility is the x. So molar solubility is the maximum amount dissolved in water. So basically the x that you solve is the molar solubility. So this x means the concentration of Pb plus 2, which is the same as concentration of sulfide that dissolved in water. So this is a concentration of lead and sulfide. This is its max that dissolved in 1 liter of water. Okay, I'm going to explain this again. It's the first problem. I want you to really understand this. So the molar solubility of lead 2 sulfide is 2.9 times 10 to the minus 14. This means that only 2.9 times 10 to the minus 14 moles of PBS can dissolve in a liter of water. It could ionize into 2.9 times 10 to the minus 14 moles of Pb plus 2 and 2.9 times 10 to the minus 14 moles of S minus 2 because they have a 1-to-1 ratio. Again, in 1 liter of solution. So this is the concentration of this and this that dissolve. This is the maximum amount that we could dissolve in a 1 liter of solution. Sounds good? Now, is it much? Not really. It's such a small amount, right? And that's what we expected because KSP was such a small KSP. So a little bit dissolves in water, but not so much. All right, ready for next problem? Let's do this. Okay, so here is our next problem. Now, when you read this problem, I ask you to figure out the KSP if that much is dissolved to make a 2.0 liter of a saturated solution. Again, what's the saturated solution? You already know this. Saturated solution means the maximum amount of solid. The max solid is dissolved. So as much as it could possibly dissolve has dissolved, and we cannot dissolve anymore. That's a saturated solution. That's a saturated solution. Now, I want you to pause me. I want you to do this problem on your own. But I'm going to give you a hint. I'm going to give you a hint before you do this problem. And here's a hint to you. Remember, KSP, like any other equilibrium constant, what do you need? For KSP, you need molarity. You need concentration in molarity. It's just like any other equilibrium. All right, don't forget. Before you pause me, don't pause me yet. You write down the equilibrium equation, write down the expression, and then go from there. All right, so hopefully this is what you did. You go zinc phosphate. Here's my equilibrium. Some of it, probably not much, will break up into zinc ion, 2 zinc, and then 2 phosphate ion. And hopefully you went that, okay, KSP is equal concentration of the zinc ion to the power of 3 times concentration of phosphate to the power of 2. Okay, now remember, this is solid, right? This is not part of the equilibrium. And as the solid goes away, this one and this one and this one is forming. So the solid goes away and some of it dissolve into ions. But the coefficient do matter. So this would be my 3x and this would be my 2x. Okay. Now in this question, they ask you for KSP. They ask you for KSP. So somehow I need to have the concentration of zinc and I need to have the concentration of phosphate. I need to figure it out. What they give you, they tell you how much of the zinc phosphate dissolve. That's great. So we know this is the maximum of the zinc phosphate that dissolves. Okay. Now remember, here's my hint. For KSP, you need molarity. So what am I going to do? What I'm going to do is I'm going to go to the next page so I have enough room. I'm going to convert that to molarity. 1.18 times 10 to the minus 4 grams of zinc phosphate dissolve. That's the maximum that dissolve. I'm going to convert it to moles. You know in chemistry, grams doesn't get you much. 386.11 gram. That's a molecular weight. Okay, this one right here is a molecular weight. I looked it up. You should definitely calculate it. So 3.06 times 10 to the minus 7 moles. Alright, what is molarity? Moles per liter. What's the liter over here? Read the question. If you read the question, it is in a 2.0 liter solution, right? So if I do that, so moles divided by liter, I get 1.5 times 10 to the minus 7 molar. That's the molarity I got. That's how much zinc phosphate dissolved in a 2 liter solution. That's how much of that dissolved in a 2 liter solution. Okay, now we can determine the molar concentration of each ion using a stoichiometry. So this is how much of the zinc phosphate dissolve, right? Now, when the zinc phosphate dissolves, remember, what I want a concentration of zinc, and what I want a concentration of phosphate. Now, stoichiometry, we're going to use stoichiometry. Look over here, you're going to use stoichiometry. When one of these dissolve, how many of zinc do you have? 3, and then this is 2. 1 to 3 and 1 to 2 mole ratio, right? So, what I'm going to get 3 times 1.5 times 10 to the minus 7. I get 4.5 times 10 to the minus 7 molar of zinc is going to dissolve. It's going to be in the solution. And 2 times 1.5 times 10 to the minus 7, which is 3.0 times 10 to the minus 7 molar. I want to explain this one more time. So what I found out, this is how much zinc phosphate will dissolve. When zinc phosphate will dissolve, you will have zinc ion and you have a phosphate ion, but you have to do the stoichiometry, because when one zinc phosphate dissolve, you end up with 3 zinc and 2 phosphate. When one of these dissolve, you have 3 of those and 2 phosphate. Okay. Alright, so now that I have that, I can go back to KSP, because we're trying to figure out KSP. KSP is concentration of zinc. Oh no, you guys can't talk to me to tell me that I just did this one wrong. It's plus 2, right? You guys knew that. To the power of 3 times the concentration of phosphate to the power of 2. Don't forget that. Write down the basics. Now, do I have the zinc concentration? I do. It's 4.5 times 10 to the minus 7 to the power of 3. Because what this is just the zinc concentration. What this is the phosphate concentration. I plug this in, but again, the equation calls for you to having it to the power of the coefficient, right? That's the equation. Times 3.0 times 10 to the minus 7 to the power of 2. When I do this, what I end up getting for KSP, my KSP is going to be 8.2 times 10 to the minus 33. Now, KSP is so small. Small KSP. What does a small KSP mean? Not much dissolve. So small KSP means not much dissolve. So far so good. Okay. Now, little side note again. This is that we got. This means this is the max it can dissolve. So this is the max zinc phosphate that was dissolved. And then it was ionized. It was ionized into 3 zinc and 2 phosphate. So we had to figure out stoichiometry, do a stoichiometry to figure out the concentration, and then plug it into KSP equation to figure out what the KSP is. And KSP is a small number. That means not much dissolved. So always write the equilibrium, write the KSP expression, put the x's, and then try to plug it in. All right, are you guys ready for next problem? Let's do the next problem. Here's our next problem. Take a minute, read the problem, and then do the problem. Pause me, do it, and then we're going to go over it. So in this problem, they ask you for molar solubility. And remember what we said. We said when they ask you for molar solubility, that's the maximum amount that has dissolved. Basically, they're looking for X. What is the max that has dissolved? They're looking for X. So hopefully you go, okay, I know how to do this. I'm going to write down the equilibrium equation. It breaks up into that and 2I minus. And this is my solid, so it's not going to be included. But when this goes away, I have this and this appears. So far so good. And you go KSP, lead to iodide is not part of it, but my is Pb plus 2 times iodide to the power of 2 because the coefficients matter. Now in this problem, KSP is given to you. What is KSP? Is 8.7 times 10 to the minus 9. Now Pb is X. I don't have that, right? Now I minus is 2x. But don't forget, so the 2x is basically the concentration. The x is the concentration, but I still have to do it to the power of 2. That doesn't change because what 2x is just means this is the iodine concentration. X means this is a Pb plus 2 concentration. Okay, so you still have to do it to the power of that. Now here is knowing your math makes a difference. So I have 8.7 times 10 to the minus 9. So this would be X. Now don't forget that. So this would be basically 2 to the power of 2 and then X to the power of 2. So what it would be? It would be 4x squared. Now if I combine all of these together, what do I end up with? I end up for 4x3. 4x3. Okay, now if you do the math and then you solve for x, again this is 8.7 times 10 to the minus 9, what do I end up getting for x? For x you end up getting 1.3 times 10 to the minus 3rd. Again, x is going to be molarity. It's going to be molarity. So now what does that mean? This is the maximum amount of lead to iodide that would dissolve. Okay, this is the maximum amount that will dissolve, which will make the same amount of Pb plus 2, but for I, it would be double of that. For I, it would be double of that. So this is a molar solubility. This is my X. This is how much lead to iodide will dissolve. And it would dissolve and it would make Pb plus 2 and it would make I minus. But you have to care about the stoichiometry and the mole ratio. But X is basically my molar solubility. Okay, let's do one more problem so you can get used to this stoichiometry idea. All right, class. So this is our next problem. So aluminum hydroxide, again, aluminum hydroxide. And hopefully you again, pause me, do this problem. The same thing before. You see a KSP problem, you go, okay, I'm going to write down the equilibrium. Aluminum hydroxide will break up into aluminum plus 3 and 3 OH minus. Okay. And then you go, I know how to do this. KSP is concentration of aluminum times concentration of hydroxide to the power of 3 because coefficients do matter. And then you go, okay, this is minus X, this is molar solubility. When aluminum hydroxide goes away and dissolve, I end up getting X and 3X. The coefficients matter. All right. Now in this problem, the KSP is given to you, right? The KSP is given to you. That's great. So because I have a KSP is 1.9 times 10 to the minus 33. So far, so good. Now, aluminum concentration, I don't have it. That would be my X, right? And hydroxide would be 3X. Okay, so this is X, this is 3X. But again, don't forget, the formula calls for you have to do to the power of the coefficient. So the 3X is the concentration, but it's only to do it to the power of 3. Okay, so I do this. Now again, this is where the math can get a little tricky. Make sure you guys get the math down. 1.9 times 10 to the minus 33. So this would be X. This would be what? 27X cubed. So if I combine everything together, it would be 27X to the power of 4. Again, what I'm more worried about right now is you guys getting the math down, because the rest, I think you got it down. So what X is going to be? X is going to be 2.9 times 10 to the minus 9. Okay. And remember, this is my molar solubility, right? This is my molar solubility. Now, it doesn't ask you for molar solubility, which is how much of aluminum hydroxide has dissolved. This is how much of the aluminum hydroxide has dissolved, right? It asks me for concentration of the aluminum ion and hydroxide ion. Okay. Now, this would be the concentration of aluminum hydroxide because it's a 1-to-1 ratio. But how would I figure out the hydroxide concentration? So this is my X, right? This is my X. What would be the hydroxide concentration? The hydroxide concentration would be 3 times 2.9 times 10 to the minus 9, which would be 9.0 times 10 to the minus 9. So, one more time. X is molar solubility, right? X is molar solubility. Now, what does molar solubility mean? It means how much of the aluminum hydroxide dissolved, right? So this is how much of the aluminum hydroxide dissolved. But when it dissolved, it was a 1-to-1 mole ratio. This is how much aluminum ion you have. But when it dissolved, you form 3 OH, right? So 3 times of that, this is how much hydroxide I would get. Now, this is super cute. Check this out. What you should do now, you should take these numbers and plug it back into the KSP and check if you get 1.9 times 10 to the minus 33. You should definitely do that. Okay? So check your work. Check your work. And how would you check it in work? Plug it back in here, right? Plug it back into these numbers, plug it back into here, and see if that's the KSP that you would get. Okay. All right. Nice job. And then next time, we're just going to keep doing these practice problems to make sure you guys get this down. Now, which means I should definitely give you a take-home problem. Okay, here's our take-home problem. It's a little more challenging, but you guys got this down. I will see you guys next time.